Welcome to Episode 8 of A Visual Approach to Optics, a Guide for Clinicians, narrated by Dr. John Gorfinkel. In the last episode, we completed 180 out of 278 slides. We finished with this slide on contrast sensitivity, in which we showed that the contrast sensitivity is higher for larger size objects in the 4 cycles per degree range than it is for smaller, finer objects with a higher spatial frequency. We can use the visual acuity to calculate the reading lens power in low vision. Kestenbaum's rule says that we need to give the inverse of the Snellen acuity as the power for the reading add in order to read 1M size print at 40 centimeters away. 1M print is a 2050 size optotype. In other words, the inverse of 20 over 50 is 2.5. That means with a 2.5 diopter reading glass, one can see an object at 40 centimeters away clearly. That is because the primary focal point of a 2.5 diopter lens is 40 centimeters in front. The question is, what add is needed to read 1M print if the visual acuity is 20 over 250. According to Kestenbaum's rule, the inverse is 12.5 to read the 1M print. Why? Because the patient needs print that is 5 times larger. Therefore, it needs to be moved to 1/5 the distance. 1/5 of 40 is 8 centimeter. 8 centimeter in front of a 12.5 diopter lens is the primary focal point of that lens. If wearing a reading glass of 12.5 diopters, one can see clearly. In other words, although Kestenbaum's rule looks like it is telling you what reading add is required, what it is really doing is telling you how close the object needs to be, because the inverse of that in using meters gives you the power of the glasses needed in order to see clearly at that distance. In other words, visual acuity of 20 over 250 is 1/5 as good as 20 over 50 vision. Therefore, we need to move the print closer to 1/5 the distance in order to get the magnification to compensate. But we need additional add in order to be able to see at that distance without any additional accommodation. We can use the ratio method to calculate the reading add power needed in low vision patients. We take the target near acuity, divide by the best near acuity, and multiply by the test distance to get the new reading distance required to get the angular magnification of the letter. We then calculate the reading add needed to be able to see an object at this distance clearly. What add is needed to read the 1M print at 40 centimeters away if the visual acuity is 20 over 200? Recall that the 1M size letter occupies a visual angle similar to a letter that is at 20 over 50 size. The target near acuity is to be able to read the 1M print, which is normally seen at 40 centimeters away. This patient's best near acuity is to be able to read the 4M print, which is 4 times larger, because the vision is 20 over 200, which is 4 times less than 20 over 50. So we take 1 divided by 4, the TNA divided by the BNA, and we get a quarter. We multiply the reading distance that is normally 40 centimeters and now get 10 centimeters. If we move this letter to 10 centimeters away, the angular size is now 4 times, and this patient will be able to see the letter. However, we need to calculate the amount of reading add required to be able to see this object at 10 centimeters away. This object will give off light with a divergence of -10 diopters at the patient plane. Therefore, the patient would require an additional 10 diopters in order to see it clearly. The reading add would be 10 diopters to read at 10 centimeters. The summary is that we move the print closer and give the reading add required to see it clearly. By moving the print closer, we increase the angular size of the print. Here we see how to set up an exam room for visual acuity testing. We have a patient at 2.7 meters in front of a mirror. This mirror is reflecting an optotype on a monitor that is 3.3 meter behind. The virtual image is therefore 3.3 meter in front. The optotype that the patient observes is therefore 2.7 plus 3.3, which is 6 meter in this diagram. We then need to calculate the size of the letter here in order to get a visual angle for testing. So if we wanted a 5-minute of arc size letter, a visual angle, and we know the distance, we can therefore calculate the height that the letter needs to be. And this can be adjusted on the monitor. Here we see the calculation, which is instructive. The 6/6 letter in meters has a visual angle of 5 arc minutes. 5 arc minutes is 5/60ths of a degree, which is 0.001454 radian. The letter size is approximately the angle in radians times the distance where the angles are small. The letter size in radians times 6 meters gives 0.8727 centimeter on the reflecting screen. In other words, the letter has to be 0.87 centimeters high. The letter that is testing the minimum visual acuity, which is a 5 arc minute size visual angle size letter. If we want to test the 6/60 letter, we need this letter to be 10 times larger, or 8.73 centimeters high. We use retinoscopy to refract a patient and determine the patient's refractive error, if any. We have a retinoscope illuminating light, which can give off divergent plano or convergent light depending on the position of the converging lens relative to the bulb behind it. Newer scopes have only divergent and plano positions. Here we show a slightly divergent light coming off the device onto a mirror reflected into the eye, which illuminates the retina, and reflected light that is now orangey red comes off the retina to be seen by the observer. Dioptrically speaking, if this is an emmetropic eye, the retina is conjugate with infinity, and the reflected light will come off with non-vergent rays, and the image will be therefore a virtual image located at infinity. The area of retina visible to the observer using the retinoscope is quite small. Since the observer is far away, relatively around 2/3 of a meter away from the patient, the area of illuminated retina visible is here. Here we see what happens in retinoscopy of a myopic or a hyperopic patient. In the myopic patient, the far point of the retina is conjugate with an image at some finite distance in front of the eye. In other words, light reflecting off the retina in the myopic eye creates a real image in front of the eye at the far point. It is a faint image, but a real image. When the retinoscope is tilted to illuminate ever inferior positions of the retina, as the light is moved from here to here, the image of the retina in space is moving up. The observer sees this image moving in the upward direction when tilting the light downward. In other words, tilting down causes image up and is perceived as against motion. In other words, the light reflex band coming off the retina is moving in the opposite direction to which the retinoscope is being tilted. In the case of the hyperope, the retina here is conjugate with a point beyond infinity, or mathematically equivalent to a point behind the eye. When the retinoscope light is tilted ever more inferiorly in this direction, the image of the retina at the far point is moving down as well. This is a virtual image and appears to be moving in the same direction as the tilt. So tilt down causes the light band to be moving downwards, and this is perceived as with motion of the light versus the tilt of the retinoscope. Here we see retinoscopy in high myopia and low myopia. In high myopia, as the light is being moved inferiorly, the retina is forming an image in space somewhere in front of the observer. In other words, as the light is being moved down, the real image is moving up in space in front of the observer. So no surprise that tilt down is perceived by the observer as image moving up, which is against motion. In the case of the mild myope, we have the retinoscope light being moved inferiorly, and the image of the retina, which is now behind the observer, is moving upwards. However, now the uncrossed rays are moving up over the observer's retina and is perceived as therefore moving downwards in space. So tilting down, in this case, is perceived as the image moving down by the observer. In other words, the band of light coming off the retina through the pupil, and this is seen as with motion. In other words, only where the image coming off the retina is between the patient and the observer will it be seen as against motion. If the myope has a retina conjugate with any point behind the observer, or at infinity, or beyond infinity, which would be a hyperope, which is mathematically like having the image behind the eye, in all those circumstances, it will be perceived by the observer as with motion. The neutral point occurs when the retinal image is in the observer's pupil plane, in which case there is no perceived motion of the retinoscopic light reflex as one tilts the light up or down over the patient's retina. Typically, the observer is 66 centimeters in front of the patient when doing retinoscopy. In this case, we have a 1.5 diopter myope, so that this patient's retina is conjugate with a point 0.66 meter away, which is the inverse of 1.5 diopter. So doing retinoscopy at this so-called working distance of a 1.5 diopter myope shows no movement of the light reflex and appears to be at the neutral point. If this patient were an emmetrope, the retina would be conjugate with infinity and non-vergent rays would be coming out of the eye. We can therefore put a 1.5 diopter lens in front of this emmetrope and create this situation. In other words, an emmetrope with a 1.5 diopter lens in front will be perceived as having non-moving light in retinoscopy. So in summary, we add plus or minus lenses in front of the eye in order to get neutralization. In other words, bring the image of the retina onto the plane of the observer. We take whatever that number is and subtract 1.5 diopters to find out what the patient needs to see at infinity. If we didn't subtract that 1.5 diopters, then whatever number we got here would show what the patient needs to see at 66 centimeters away. So a 1.5 diopter myope observed by a retinoscopist from 66 centimeters away would be at the neutral point without any additional lenses. Therefore, the required lens for this myope to see at infinity would be minus 1.5. If, on the other hand, we needed an extra 1.5 diopters in front of a patient with unknown refraction to get neutralization at this distance, we would then have 1.5, we would subtract 1.5, which would show that the patient needs no additional lens to see at infinity. If we determined that we needed 3 diopters, for example, to get neutralization when observed at this distance, then this patient would need 3 diopters minus 1.5, which would be 1.5 diopters to see at infinity. This patient would be a hyperope. This is what the light streak looks like in retinoscopy using a streak retinoscope, which is another way of saying we have a filament with a long axis that gives a band-like area of light with a long axis in one direction and short in the other. The light reflex is that part of the light that's coming out of the pupil. The intercept is part of the retinoscope light that overlaps the eye just outside of and adjacent to the pupil. The higher the ametropia, the narrower the light reflex looks as compared to the intercept. As we approach neutralization by adding more corrective lenses, the light reflex widens. As we get closer to neutralization, the light reflex widens even more until it fills the whole pupil and does not appear to move with the tilting of the retinoscope. If the eye has astigmatism and the light reflex is not in line with the astigmatic error, then the light reflex appears to be broken away from the orientation of the intercept on either side. One would then rotate the intercept to match the axis of the intrapupillary light reflex and then add lenses to attempt neutralization. This can be done in the first axis and then in the other axis at 90 degrees away, and 2 different numbers will be obtained in each axis. The Jackson cross cylinder is used to refine correcting cylinder when refracting. The cylinder is made of 2 equal plus and minus cylinders at right angles. Most commonly, a quarter diopter is used, but one can use a half diopter or 1 diopter as well. Here we show the appearance of the Jackson cross cylinder with a handle and the markers indicating the 2 different axes. This is the representation. We have a quarter diopter long axis this way and a minus quarter diopter long axis that way. We already know that we can rewrite this as a spherocylindrical notation in which we can either assume a minus 2.5 diopter sphere with an additional half diopter in this axis, or we can assume a quarter diopter sphere with an additional minus 1/2 diopter in this axis. It can also be described as 2 cylinders of a quarter diopter here and minus a quarter diopter there. That would be the 2-cylinder notation. We can use the cross cylinder to refine cylinder axis. We align the bisector of the cross cylinder with the astigmatic air, and we twirl it back and forth, effectively flipping the cylinders from +1/4 and -1/4, and observing in which orientation the patient sees better. If using plus cylinders to correct the patient, then one rotates the correcting cylinder that has been placed over the patient's eye towards the orientation of the plus cylinder in the Jackson cross cylinder, and repeats the procedure until an endpoint is reached, at which point the patient will say that either flipped position of the cross cylinder gives equal vision. The reason this works is because the misalignment of the correcting cylinder from the axis of the eye error cylinder forms new cylinders. These cylinders are later corrected with the cross cylinder. Here we show the patient has a minus eye error cylinder at 100 degrees, and we have attempted to correct the patient with a plus cylinder at 90 degrees. Because there is a misalignment, there are induced additional cylinders created as shown. One plus cylinder at 50 degrees here, and an induced minus cylinder at 140. These new cylinders are induced at 45 degrees on either side of the bisector of these two cylinders. The bisector is at 95 degrees, halfway between 90 and 100. The new cylinders are therefore at 50 and 140 degrees as shown. By aligning the cross cylinder with the correcting cylinder at 90 degrees and flipping back and forth, in the position shown here where the plus cylinder is here, it adds to the induced cylinder, which is close to it here, shown in red. If we were to flip this around by twirling this cross cylinder, then the minus cylinder would appear in this axis and somewhat negate the plus cylinder that has been induced before. And similarly for the other axis. So therefore, in one position, the cross cylinder increases this induced cylinder and makes vision worse, and in the other position, the opposite cylinder of the Jackson cross cylinder partly neutralizes the induced cylinders from before and improves vision. We would then move the correcting cylinder. If it's a plus cylinder that we're using in our trial set, we would move it towards the position where the plus cylinder makes vision better. In this case, the plus cylinder in this axis would make vision better instead of in this axis. So we would rotate the correcting lens towards this axis here. And we would keep repeating this until the patient reported that the flipping back and forth gives equal vision, at which point the correcting cylinder would likely be in line with the minus eye error shown. We can then use the Jackson cross cylinder to refine cylinder power in the correcting lens. Instead of aligning the bisector of the cylinder with the correcting cylinder that we've placed before, we align one of the two axes that are marked on the Jackson cross cylinder with the correcting cylinder that we've previously placed. We twirl the handle to flip the Jackson cross cylinders back and forth so that the minus cylinder is in line with the correcting cylinder or the plus cylinder is in line with it. One of the positions will make the vision better and the other will make it worse. In one position, we have the astigmatic cone of Sturm being reduced in size, and in the other position, we have the astigmatic conoid of Sturm increased. When the conoid of Sturm is made longer, the circle of least confusion is larger, and the image appears more blurred. In the better position, the circle of least confusion is smaller. Once we have adjusted the cylinder so that rotating the Jackson cross cylinder results in equal vision in both positions, we have reached the end point of adjusting cylinder power. In this situation, the two lines of the conoid are on either side of the retina and get flipped back and forth, but the circle of least confusion is the same in both positions. And this is the diagrammatic equivalent of the endpoint of refinement of cylinder power. The images will be said to be equally clear or equally blurry in either position. A detailed discussion of the technique of retinoscopy is not being presented in this series. Optical instruments, the direct ophthalmoscope. Here we have an illumination device being reflected off a mirror onto the retina. Here we have divergent light coming off the bulb. This light illuminates the retina. The retina then gives off light that is refracted and exits the eye. If this is an emmetrope, then the retina is conjugate with infinity, and the rays that leave the eye are non-vergent. These rays then enter the eye of the observer. If the patient or the observer have an eye error, this can be compensated for with a lens in the retinoscope device to create the equivalent situation seen here. In this situation with non-vergent light, the observer does not need to accommodate in order to see the light clearly if the observer is an emmetrope as well. Since the retina, which is the object, is at the primary focal point of the emmetropic eye, the lens system of the eye acts as a simple magnifier. The magnification is 1/4 of the power. If one considers the power to be, in a simplified form, 60 diopters at the front of the eye, then 1/4 of 60 is 15 times. In other words, the visual angle here, seen by the observer, is 15 times what the retina would look like if there were no eye optics in between the retina and the observer, and the retina were being observed from 25 centimeters away. Here we have an indirect ophthalmoscope in which the observer is wearing an illuminating device in the headpiece, which is illuminating the retina. The retina now gives off light and is the object being observed. Here we show light coming off the top and the bottom of an area of the retina. If the patient is an emmetrope, the light will leave the eye non-vergent, since the retina is conjugate with infinity. This non-vergent light enters a handheld lens, which is usually a 20 diopter power lens. This lens will then create an image at its secondary focal point, which is 5 centimeters behind. Because this is a real image, it is inverted. It appears to the observer to be located within the lens, but dioptrically is actually floating in space 5 centimeters in front. In order to allow both eyes to see simultaneously through the patient's dilated pupil, it is necessary to reduce the effective separation of the two eyes of the observer. Typical interpupillary distance is 60 millimeters. By using prisms with total internal reflection adjusted in such a manner as shown, effectively one can reduce the distance between the two patients' pupils to 1/4, which would be 15 millimeters apart. Rays that are coming in, which are separated by 15 millimeter, end up entering the observer's eyes, which are now 60 millimeters apart. The image is located fairly close to the headpiece, so that accommodation could be a problem in certain age groups. As a result, an additional 2-diopter lens is placed inside the headpiece to allow easier viewing of the divergent light coming off the real inverted image.